So thank you all for joining me for the first webinar for wind empowerment this year. We'll be hosting a series of webinars this month, and we will make it a monthly venture. The next webinar will be on September 16th, and the Wind Aid Institute will be presenting. More information about that presentation will be sent out to you in a week, along with a flyer for the upcoming ones. The webinar will be an hour long with 15 minutes a question and answer session, and then an additional 30 minutes will be given for those that want to stay on for more questions. For those that are not able to participate, the presentations will be recorded and uploaded to the website so they can view them. And if you'd like to be a presenter for our webinars in the future, feel free to email me at jessica@windaid.org, and then I'll get you on the list. And now for a presenter this evening, I trust that you all read Aran's incredible bio, but if you didn't, he's a superhuman who is spreading the word about the small-scale wind turbines to the Hugh-Pigott design worldwide. And so now Aran will take the lead.
Thank you very much for that introduction, Jessica. I'm not too sure about the superhuman part, but thanks anyway. Hi everybody. I'm talking from Glasgow today. The weather's good. I'm going to give an hour-long talk about market assessments for locally manufactured small wind turbines, drawing on a case study in Ethiopia from a project that was completed last year, and an academic piece of work that I've been working on. So today I'm going to go through, introduce myself and the project, give a bit of a background to what's happened, give a context to energy use in Ethiopia and small wind turbines as a solution, and then go through the process of conducting a market assessment, the input parameters such as costs and energy resources, the analysis in optimization software called HOMA and GIS mapping, coming out with some results and conclusions of if wind turbines are suitable in Ethiopia and where, and finally some next steps for the project in Ethiopia and wind empowerment in general. There is quite a big section for questions at the end, but if you don't understand anything, and as there's only a few of us, feel free to jump in if you want clarification on any of the slides. So as an introduction, that's me. I studied engineering, and after graduating set up a workers' cooperative called V3 Power, who build and install and run courses about small-scale wind turbines to the Hugh-Pigott design. We're based in Nottingham. In 2011 I started a Masters in Renewable Energy at the Centre for Alternative Technology in Wales. And the dissertation for that Masters is the content for what this presentation is about, small wind turbines in Ethiopia. And since November last year I've been on the board of Wind Empowerment as the funding coordinator. And we're currently organising the conference in Athens, which is November this year, and we're looking to get set up as a legal entity in the UK as a charitable incorporated organisation. So to give you a bit of a background, V3 run courses in the UK and in Europe, and this course is run in Germany. That's me, Tom and Andy running this course in Kassel in Germany in summer 2013. And this guy is Gulama, who is part of an Ethiopian NGO called Sahey Solar, who run solar PV projects in Ethiopia, rural electrification of health centres. And he was very interested in the wind turbine design and the course, and he invited us to Ethiopia to run a course out there. So in December 2013, myself and John Tumanik-Leary went as part of Wind Empowerment, and we ran a course at Arbor Minch University, which is in the south. Most of the materials were bought locally, including the wood, the copper. Sahey Solar were actually importing some solar panels and some batteries to run a solar project out there. So some of the materials were actually imported from Germany, but most of them were purchased locally. And in a university laboratory, we built a 1.8 meter 300 watt turbine and installed it locally on the campus. Unfortunately the site didn't have too much wind, so we didn't get to see the turbine spinning, but it was a very useful educational tool with 26 students that we taught very inspired and interested in wind turbine technology, which hasn't really been done a lot in Ethiopia. So at the time I needed a dissertation for my master's, and I was interested in investigating whether these small wind turbines would be appropriate for the Ethiopian context, and that's where it's led me to this presentation. So I'm going to start with a context of energy access in Ethiopia and looking at small wind turbines as a solution before going into the actual data collection and the market assessment itself. So this graph shows how electricity use per capita along the x-axis, how that increases. That affects the Human Development Index, which is a UN measure of quality of life. I think it takes into account mortality rates, birth and death rates, education rates, and this graph shows that as your electricity use increases, your quality of life or your Human Development Index increases as well. There's a couple of interesting points about the graph. After about 4,000 kilowatt hours per and Japan are using a lot of energy, but their quality of life isn't increasing very much. And the other thing to note is that developing countries only need a little bit of energy to increase their quality of life quite significantly. So Mexico, for example, is only using about 2,000 kilowatt hours per year, but their quality of life isn't that much below the UK. The other interesting point to note about this graph is that Ethiopia is right at the bottom here with an extremely low Human Development Index and an extremely low per capita electricity use. In fact, the UNDP estimates that about 86% of the population don't have access to electricity in their homes. So it's only 14% that do, which is quite a big figure. Within Ethiopia, they've got a huge amount of renewable resources. In fact, about 90% of their grid comes from hydropower, and you can see the exploitable reserve here is quite huge. The grid electricity is mostly hydro, and the off-grid for those millions of people that don't have it is mostly solar home systems, which are small PV panels providing lighting and phone charging. So the government's recognized the need for renewable energy, and it wants to expand electric power generation from renewables fivefold over the next 5 years. And they've also noticed that wind power is viable in Ethiopia, which we'll see in the next slide. This map shows wind energy in Ethiopia at 80 meters, and you can see in some areas there's some quite substantial average mean wind speeds of 9 meters per second. And this is recognized at the utility scale with 2 wind farms being installed recently in Ethiopia. One at Ashigodo, which is 120 megawatts, which at the time of writing the dissertation was the biggest in Africa, and the second at Adama, which has got 2 stages. And from this we can see basically that wind power is feasible in Ethiopia. However, no one's really using small-scale wind power, which were the reasons for wanting to do the project in the first place. So this graph shows that at smaller scales, wind is quite competitive economically with other technologies for rural electrification. This measure is the levelized generating cost, which is the dollars project, and the x-axis shows a different power generation capacities. So you can see at smaller capacities, wind is cheaper than PV and hybrid, and also cheaper than PV, and a lot cheaper than diesel. Although hydro is the cheapest and always will be the cheapest. This graph might be slightly old because in recent years the cost of PV has decreased quite a lot, so PV is becoming a lot more competitive with wind. But wind is still one of the cheapest options for rural electrification. So of locally manufactured small wind turbines for rural electrification, or as you guys will know better, known as the Hugh Pigott wind turbine. So I don't need to go over this too much because you've all been working in it in your careers, but it's an open source design which uses locally available materials and is easy to build. It supports the local economy and creates jobs. Especially in Ethiopia, they're interested in this value chain, whereas most of the options for rural electrification are PV, which they have to purchase from China or from Germany, which sends money out of the country. And there's quite a big problem in Ethiopia with a limited amount of foreign capital, and purchasing PV from abroad reduces that, whereas manufacturing locally increases the local economy. So you guys know all about the benefits of Hugh Pigott wind turbines, and there are several groups all around the world manufacturing wind turbines locally, and several groups in Africa. You can see here from Tanzania, Mali and Malawi and Kenya, in fact. So wind turbines are built and installed in East Africa, and we wanted to investigate it in Ethiopia. So looking at the existing literature, the academic literature of what's already been looked at for rural electrification in Africa, there's quite a few economic analyses of what the most feasible technology is for different parts of Africa. And you can see this map here, which gives areas where PV is more suitable, grid connection is more suitable, or this map here which shows micro hydro and mini hydro, and also diesel generators as well. So there's a lot of these maps around, but nothing that I could find that shows small wind, or indeed locally manufactured small wind. There's also been some market assessments done by John, who's here today, about Nicaragua, and there was another proposal for a market assessment to be done in Brazil, but I'm not too sure what came of that. And there's none of small wind turbines in Ethiopia, as I know of. So that gives a bit of a background to the project and a context. We're going to talk now about what's involved with a market assessment. And these slides are actually John's. I'd like to acknowledge that. Thanks, John. So when you're looking at a market assessment, you're wanting to know where the wind resource is. You don't want to install wind turbines in areas of low wind. The power available in the wind is proportional to the velocity cubed, so it's a lot more variable as compared to PV. Also, where do people live without access to electricity? It may be that people don't live in windy areas, which is often the case, but there might be places where people do live where it's windy enough for wind turbines. And how viable are other power generation technologies, and what's the cost of other generation technologies? Because people will always want to choose the cheapest technology. And finally, what are the barriers facing the technology and how can they be overcome? So this flowchart just gives a few of the questions that you want to be thinking about before you even start a market assessment. Firstly, are there sufficient solar or hydro resources to comfortably meet demand throughout the year? If there are, it's likely they'll be cheaper, and small wind turbines aren't the right technology for this context. Is there reliable wind data? If no, you should probably invest in better wind mapping, because you really need to know the wind before you start. Are the wind resources above 4 meters per second throughout the year? If they're not, you want to look at whether the solar and hydro resources are available in the low wind season. If they're complementary, then wind is a good idea. If they're not, then wind's probably not. Next, is there a critical mass of potential users in this region to make maintenance services cost effective? If there's just one guy living on top of a hill 100 miles away from anyone, it's probably not going to be cost effective. But if there's a community of people all needing wind turbine and you can make the maintenance work, then it will be cost effective. Other things to look at is whether there's environmental hazards, whether there's existing transport infrastructure, are the buildings close enough to link via a microgrid, And is the wind resource high enough or topography simple enough that individual site assessments aren't necessary? If the answers are yes to a lot of these questions, then it's good to conduct a full market assessment for small wind turbines. I'm going to go now into what actually happened in Ethiopia, the data we collected and the results that we found. So the methodology was to collect data to do with system design. That's what loads are the system going to be providing, and that's specific load profiles, and what technology is going to be used with the wind turbines. In this case, batteries, solar PV and diesel generators. A big part of the analysis is the energy resources. What's the solar resource, the wind resource and the diesel? And obviously, because it's a market assessment, what are the costs? Business costs, operation and maintenance, and economic parameters such as interest rates on loans, etc. So the main data came from primary research fieldwork when we were out in Ethiopia, asking prices from local suppliers and having interviews with Ethiopian NGOs and academic institutions. And wherever possible, this was cross-correlated with real-life data from journal papers or data from wind empowerment members. I'm going to show you a few websites where you can find very good wind and solar resource, the International Renewable Energy Agency, the National Renewable Energy Laboratory in SENA, and also the World Bank. Finally, the data was all analyzed in HOMA, which is a system optimization tool which gives the levelized cost of energy, and then some GIS mapping, which actually tells you where in the country the wind turbines are suitable to be implemented. So the primary research was actually a big shopping list in this place here, which is Mercato, the biggest open market in Africa, where you can get pretty much everything you need as long as you've got a guide. We managed to get prices for steel, copper, wood, resin, all the components of a wind turbine apart from neodymium magnets and charge control circuits. There's already people installing off-grid solar systems, so batteries and cabling were all able to be found, so everything apart from the magnets. For business costs such as local wages, transport costs and costs that are needed to model setting up a business in Ethiopia, we had interviews with renewable energy practitioners, so companies that are running solar systems, installing solar systems or microhydro. And as I said, any data was correlated with peer-reviewed papers. So the first piece of information required is the load profiles, and this needs to be fed into HOMA on an hour-by-hour basis, what loads are required. And these were found for a commercial centre in the Verda district, which is eastern Ethiopia. The reason we used a commercial centre is that we wanted to model productive uses of energy. And these are uses that allow economic development as opposed to communication and education energy sources, such as lights or phone charging. And there's an interest in using these wind turbines, the 1 kilowatt machines, to provide a productive use of energy so that people can actually earn some money and develop the local economy. So this is the load profile, and I was a bit surprised. It's actually for a beauty shop and a barber shop, basically, with a fridge, a fan, exterior lights and interior lights. I didn't think I'd be putting all this effort to make sure that people had haircuts, but it turns out when you speak to a lot of business entrepreneurs in Ethiopia, it's a really solid business model, a barber shop. People always need haircuts and people always want to look good. So in a rural area, quite a guaranteed source of income is providing energy for a barber shop, and you'll see a lot of solar-powered barber shops springing up everywhere. So that was what the load profile was for, a commercial centre. This is an outline of the choice of technology. A locally manufactured small wind turbine of 1 kilowatt. We used the oh, sorry guys. Okay, we used the power curve from the French group TL, starter voltage of 48 volts, and estimated lifetime of 20 years, which I agree might be slightly high given Ethiopia's dusty conditions, and the range of costs, which I'll talk about in the next slide. In the literature review, it was found that wind turbines work well with solar panels in hybrid with a diesel generator as a backup. So the system I was modelling was about 400 watts of PV included in the 1 kilowatt wind turbine with a 3 kilowatt diesel generator as backup, with 4 batteries to store the power and an inverter. And the costs are outlined here, which were fed into Homer for the modelling. So this slide outlines the costs of the wind turbine. And if we start down here, there's different elements to installing a wind turbine. The first is the turbine materials, which were found from components in Makato, the capital. The red element is the tower, which is a similar cost to the turbine materials itself. The third is the electrical system, which might look small here because the batteries and the inverter are treated separately in Homer. The next element is the business costs, and these include rent on a premises, admin wages, and repayment on loans for tools. And we did our best to model setting up a business in Ethiopia and the costs that would entail. And finally, the manufacturing and installation costs. We took them from Blue Energy in Nicaragua, who outlined the number of man-hours required to build a turbine, and then multiplied that by local wages to get an idea of the human cost of building a wind turbine. And for each of these, there's a low sensitivity and a high sensitivity value. And this is to model an increase in component costs due to inflation or world prices increasing. It's also a reduction in costs through a reduction in business costs through bulk purchasing and specialization. So the idea is if you're building 10 turbines, you can buy all of the equipment and the components all at one time, which will give you savings. And as you're building more turbines, you become more specialized and the labor costs reduce. So that's the reasons for these low and high sensitivities. And then finally, there's three sets of costs which relate to the distance between where the turbine is manufactured and where it is installed. And these different costs relate to the engineer's time to travel to the site. And a low distance to site is modeled at half a day's travel, medium is 1 day's travel, and high distance is 2 days' travel. And so that doesn't have too much effect in the installation, but as we'll see in the next slide, it does have quite a big effect in the operation and maintenance. So this has been modeled as material costs, which is replacement of parts and any new components that have to be purchased to keep the wind turbine up and running, and also the travel and labor costs. And you can see in the operation and maintenance it makes quite a difference. If the technicians have to travel for 2 days to the site, their wages become the main part of the operation and maintenance costs. And this becomes quite significant when we see the results in Homer. So those are the costs of the wind turbine and the economic parameters. The next factors to consider are the energy, and that's wind, solar and diesel. So this is the wind resource from a map from Senna, which is modeled at 10 meters above ground level. You can see that it's quite variable across Ethiopia. We're modeling tower heights of 12 meters and 18 meters. So we used log laws to extrapolate from 10 meters up to 12 and 18 meters, which increased the average wind speed slightly from 10 meters. And in Homer we need a sensitivity So using this map, we use the sensitivity from 3 meters per second up to 6.5. Not really disregarding anything below 3 because it's not really worth building wind turbines from that. The sources of data for the wind resource are IRENA and GeoCatalog, and I hope this works. I'd just like to show you quickly these websites because they're really quite I think they're quite useful. So this is IRENA, which is an international renewable energy agency, and you've got a map of the world, and you can start with solar, and it gives you several data sets for solar resource. That's 3-tier. This is a global NASA database, and for a start you can get all your solar data from there. It also has several wind data sets. So this one is 3-tier, quite a famous map, and this is at 80 meters above sea level. So you can see this view of Africa. Somalia is really the place to build wind turbines, so is Mauritania in the Sahara Desert here. If you're in the Congo, I wouldn't think about wind turbines, and South Africa and lower Africa, Southern Africa, would maybe need some more analysis. But there's quite a few different sets of wind data. That one's just for East Africa. And you can click on any part within that, and it gives you quite a lot of information about the wind resource there. What's also useful is that you can get a world database on protected areas. You can also input the transmission lines. So this is the grid over Africa, and you wouldn't want to build wind turbines where they've got the grid. It's unlikely that you would, and this gives a map of where the transmission lines are. Also gives land cover, so that you can see what the land is, whether it's forest or irrigated croplands. So quite a useful resource, IRENA, and it's free. The other one is GeoCatalog, which has all the same data sets, but it's also got research projects. So if you have a look here, you've got a global atlas for bioenergy, for geothermal, and for what we're interested in, solar and wind. And each map, you can click on the interactive map, or you can actually download the data sets for use in GIS mapping software. But what's interesting here, I've searched for diesel in Africa, and there's the results of research projects, and this is for the whole of Africa, the estimated cost of electricity delivered by a diesel generator using the diesel price for each country and taking into account the cost of diesel transportation. The one I've got here is the map that I showed you earlier, which is the modelled most economic rural electrification option. So that takes into account grid extension, mini hydro, diesel generator, and that's for the whole of Africa. And you can download that and have a play with it. It was these maps that got me excited, really. This tells you where micro hydro is a good idea, where the grid's a good idea. Well, I can't find any of these maps for small wind power, and hopefully that's something that Wind Empowerment can do, is that we can publish one of these maps, ideally of the world, where we can say in these areas small wind is appropriate. So some really good resources there, IRENA and GeoCatalog, for the solar and wind resource data. Another aspect to look at is the seasonal profile, which actually varies quite considerably in Ethiopia. Divided the country into grids, and for each one had a look at the seasonal profile, which you can get from IRENA and those GeoCatalog data sets. You can see in the west of the country there's quite a flat profile with low wind in August, whereas to the east there's a much more pronounced varying seasonal profile with higher winds in June and July. This is important to compare with the solar, which we'll come on to in a minute. Another aspect is altitude, and this graph shows that as the height above sea level increases, there's a reduction up to about 30% of power in the wind, and that's due to the density of air decreasing. This is quite significant in Ethiopia because it's quite a mountainous area. There's people living at about sea level, and there's people living at about 3,500 meters above sea level. And when you run the altitude in Homer, it really makes quite a difference, and it's important to take into consideration when you're doing a market assessment. So the next aspect is solar resource, and you can see in Ethiopia the solar resource varies quite significantly as well. In the north and in the central, there's a high of 7 to 7.5 kilowatt hours per meter squared per day, and then in the southwest it's more rainforest, and the cloud cover means it goes down to about 3 to 3.5 kilowatt hours per meter squared per day. And that was the sensitivity that we used for Homer, 3 to 7 kilowatt hours per meter squared per day. As I said, it's important to have a look at the seasonal comparison between wind and solar resource. And in some areas of the country, it's really quite complementary. The wind is high when the solar is low, whereas in other areas of the country, they're pretty much the same. Both the wind and the solar reduce in the summer, and in these areas of the country, wind turbines aren't really suitable because you can get as much from the solar as you can from the wind. However, if the wind's really high when the solar's low, then that's a great place to install a small wind turbine. The final resource, which is used for off-grid energy, is diesel. And these are the costs of diesel from the World Bank for the last 4 or 5 years. And you can see they've been steadily increasing. And to get a sensitivity, I've just assumed a linear increase to make a prediction for the next 3 years of what the diesel price will be, assuming that it goes from 0.9 to $1.3 per litre. I agree that a linear estimation might not be accurate. Diesel prices are prone to world fluctuations, and it might be more exponential, but it's a good estimate. The other thing that's interesting about diesel prices is how it varies geographically. This is another one of these maps, and it shows how the diesel price varies with proximity to a main road. So the further the transportation carrying the diesel has to travel, the more expensive the diesel is, up to maybe 5 times the price in some areas, which is an important consideration, not just for the price of diesel, but as we'll see, for the price of operation and maintenance for wind turbines. Because if the diesel has to travel far and the costs are high, then it's the same for wind turbine components and wind turbine engineers. And if you're far away from a main road, then those costs will be high. Okay. Another aspect which isn't taken into consideration in Homer, but it's still important, is lightning. Wind turbines often suffer from lightning strikes, and this map shows where in the world lightning strikes are. And it's worth investigating for a market assessment whether there's a high prevalence of lightning strikes, and taking that into account, maybe increasing the failure rates due to lightning as a result. Okay, that's all the data collection, and that was then fed into Homer, which is a optimization tool. It gives various simulations and various optimizations, and the output that we're interested in is that it gives a levelized cost of energy. Now, I'm sure everyone here today has probably used Homer quite a lot, but for the benefit of the webinar video, it's going to quickly show you how Homer works. Over here you have all your inputs for PV, wind turbine, batteries, inverter. You start with your load profiles and you input them hour by hour, and it adds some random variability to give a realistic load profile over the month and the year. and then it analyzes what load is required each hour. You then put information about the technology. You have details of a power curve. This power curve was taken from the testing of a 1 kilowatt turbine done by the French group Thiel. Sorry if I've not pronounced that right, Jay. Their testing was actually of a grid tie machine, and the potential that grid tie machines can spin faster. They're not tied by the battery, so there's a potential that they're a bit more efficient than a battery machine, which the Ethiopian one we're modeling would be. So this might be overestimating slightly, and basically the more power curves we have of wind turbines, the better. Each one is unique, and one of the first things for doing a project in Ethiopia would be to build one locally and get a power curve. So you can put elements for the wind turbine here. Here's the quantity, the capital, the replacement, and it allows you to input sensitivity values. So the sensitivity values come as cost multipliers. So as I said, in the worst case, the wind turbine costs more to produce, and this is outlined as a cost multiplier of 1.43, and the high operation and maintenance costs are outlined as a cost multiplier of 2.38, and that becomes quite important in the analysis. You can also input the solar resource taken from the websites that give the solar resource, the wind resource, and the diesel. And then it makes an optimization of what your most efficient system is. So here, where the global solar is 6 and the wind speed is 6 and all the cost multipliers are all 1, the most optimum system is a wind turbine with the diesel and a battery and an inverter, and it tells you the cost of energy, which is $0.6 per kilowatt hour, and then the second most optimum and the third, etc. And if you're in a place where the global solar is slightly higher, then it suggests that a PV wind turbine and diesel hybrid is most sensible. So that's the optimization. And then the sensitivity gives a surface plot. So along the bottom you have wind speed, and along the side you have global solar. So where your wind speed is low and your solar is high, in this red area, this is most suitable for a PV and generator system, so no wind turbines. Where the wind speed increases, this green area is more suitable for a hybrid system with a wind turbine, a PV, and a generator. And then finally, where the wind speeds are very high, the Homer suggests that in this area, just a wind turbine with a generator is most efficient. So, as I said, I know you've all used Homer before, but it's a really great tool for analyzing off-grid systems. So if we go back to the surface plot, global solar along the side and wind speed along the bottom, we're interested in this barrier between PV and introducing a wind turbine. We can see when all the cost multipliers are 1, at a wind speed of 5.5, it's always more economical to include a wind turbine in the system for whatever global solar there is. So even if the global solar is very high at 7, as long as the wind speed is 5.5, it's more economical to include a wind turbine. So that's for all the cost multipliers of 1. If we now have a look at an increase in the cost multipliers, so this is still wind speed along the bottom, but the capital multiplier along the top for the wind turbine. So when the wind turbine is at its most expensive, at 1.43, it's still economical to introduce a wind turbine to the system, but the wind speed for introducing it has increased to 5.9. So half a meter per second doesn't make that much difference. But what's interesting is when we have a look at the operation and maintenance cost multiplier. So again, wind speed is along the bottom, but along the side is the operation and maintenance cost multiplier. This is effectively the distance to site. This is low distance to site, and this is high distance to site. We can see that now, if the distance to site is very high, the wind turbine is never economical. Even if you have a 7 meter per second wind, even if you have really high wind speed, it will never be economical to include a wind turbine because you've got to travel so far and the cost of traveling is high. So the result of this is if the travel distance to the site is more than 7 hours, operation and maintenance costs make the wind turbines not cost effective. So that's quite useful using Homer to get some results out of that. In the short term, we want to be minimizing the distance between where the maintenance team live and where the wind turbine is installed. So that's the analysis with Homer. The next analysis is the GIS filters. And this is looking at maps of the country to find out where the natural resources and everything else that's been considered make wind turbines suitable for installing. And we're looking at aspects like electricity, access to the electricity grid, distance from a transport network, and any areas with cheaper diesel or PV. So this is how it was done. I downloaded the solar resource maps and the wind resource maps into GIS software. I made a grid over Ethiopia, and then for each grid square, you have a look at what the solar resource is, and for this one, the solar resource is between 6 and 6.5, so that gives the Y coordinate, and have a look at the x-axis, which is the wind speed. For this one is between 5 and 5.5, that gives the x-axis. These give two coordinates on the Homer surface plot, and then that square would be plotted on as a wind PV generator system. That was repeated for all the squares. It's quite a lot of work and it's quite a slow way of doing it. I had a look on the forums to try and find if there's a way within the GIS software to compare this value, and then from a lookup table plot it on a pixel level, which is ideally what I'd like to happen. And if anyone has any suggestions on how to do that, I'd be grateful to know how. But as it was, I did it by hand pretty much and came out with this output. So for the gridded Ethiopia map, in these red areas, PV and a generator is suitable for the system I've modeled. In the green area, a hybrid PV and wind turbine is suitable. Turbine and generator is suitable. In the southwest, the wind resource is so low and the solar resource is so low that actually a generator is most suitable. When I say most suitable, I mean most economic. So within these grid squares, anything that's green or blue should be investigated in more detail. Looking at other aspects of the maps is the grid, the population, and areas of civil unrest. So if you have a look at this map here, the blue is the national grid, and anyone within the national grid is unlikely to get wind power. The national grid is really cheap. It's from hydro, which is one of the cheapest forms of electricity, and is also heavily subsidized by the government. So anyone in these areas is unlikely to be able to afford a wind turbine. The other interesting part is population. These red areas are high population and the white areas are low. So if we go back to where most of the wind is suitable in the south and east, this is this part highlighted here. And you can see hardly any of these areas actually have the grid, which is favorable for wind. And it's unlikely they're going to get the grid because the population is quite low, in some areas extremely low. But there are areas of population within this that aren't connected to the grid, are unlikely to get the grid, and the wind resources are suitable for them to have wind turbines. The final graph well, the final map, should I say, which sums up the dissertation quite well, is this map from the British Foreign and Commonwealth Office, which advises on travel to Ethiopia. And the red areas are advised against all travel due to civil unrest, terrorism, threat of kidnapping. And there's a seemingly apparent correlation between areas of the country that don't have access to the grid and areas of the country that have a high risk of terrorism. And you could argue that these are linked, that no electricity is increasing poverty levels, and that's increasing civil unrest and terrorism, and that wind turbines could play a part to reduce this risk of kidnapping and civil unrest. However, in the short term, I think the main implications are that any wind turbine projects in this area are probably going to be more expensive for insurance and added security for the project. So the advice would be to go to where it's safe to go, for example Jijiga, where there is national grid for building the wind turbines, and then move out from there and start with maintenance service centres as you go. So coming to the end now, draw some conclusions. For the systems that we've modelled, we've managed to see that including a wind turbine in a system is economical in Ethiopia in areas of annual wind speeds of more than 5.5 meters per second. And these areas do exist, and so there are places in Ethiopia that building wind turbines are suitable for. However, operation and maintenance costs means that if the site of installation to the site of service is more than 7 hours travel, then they're going to be less cost competitive, and you might as well go with solar or diesel, in fact. A few aspects to bring out of that. The wind resource is highly variable, both space and time. The power is proportional to the velocity q, that's why V3 is called V3. So in those squares that we've identified, we need more detailed wind data in regions of high potential. And ideally, individual resources assessments are necessary for any new projects. You don't want to waste your time in putting a wind turbine in an area where it's not going to spin. The high maintenance requirements are a big theme of the conclusions. They increase the cost and reduce the viability of a project if things are going to go wrong. So to combat that, you need to reduce the probability of failures, have a look at quality control for local manufacture, and ideally you want maintenance services to be available locally. There needs to be a critical mass of users, and there needs to be local technicians that know how the turbines work and that can fix them, and that can travel cheaply to even the most remote communities. So the distance between the service centre and the turbine is as small as possible. And this can be achieved by local manufacture, which shortens the supply chain for spare parts. So one of the next steps is, within that map that I've given, a local market assessment needs to be done, not just for wind resource, but looking at the ability to pay, the availability of microfinance if people can afford loans, and the willingness to pay for electricity. And maybe that can be increased if there's an offer of productive uses of energy which can increase local economic development and people can get jobs from the power that the wind turbine is producing. But that involves quite a lot of community organisation, and there are cultural factors between and within communities and potentially environmental hazards. This drawing to a close, the further research needs to look into ability to pay, whether people can afford wind turbines, and investigate financial mechanisms such as community ownership or pay-as-you-go schemes, people paying with their mobile phones for the kilowatt hours, and not just from the user side but also the building and implementing the wind turbines. Investigate successful business models. Is it a cooperative? Is it a private company? How many people do you have in the organisation to build wind turbines? Also look at the cost of diesel varying with the vicinity to the road network, and looking at different load profiles. We only looked at a commercial centre, and we wanted to also look at potentially institutional energy such as health centres or schools, and also domestic level energy supplies. But again, how are you going to pay for it, and how is it going to be self-sustaining financially in the future? So in terms of next steps, for the Ethiopia project, Wind Empowerment are going to be conducting a more in-depth market assessment for Ethiopia. The research at the moment is based on, well, it's an academic research, and that needs to be put into more accessible language for NGOs to use within Ethiopia. And then Wind Empowerment will be conducting pilot projects to build and install wind turbines as part of a course, training local technicians into how to build and install them. And we'll be recruiting a team later this year to run courses from our membership groups. And we've identified partner NGOs for initial projects and continuation. In terms of next steps for Wind Empowerment, well, I believe it could be possible for Wind Empowerment to offer market assessment as a consultancy service to NGOs and governments. There's a lot of wind-related projects that are being conducted but without the research done beforehand, and Wind Empowerment are in a position to offer advice and consultancy to make sure that any money spent on a development project is spent well and the project's carried out to the best of its abilities. And also that if the market assessment comes out and says that wind turbines aren't a suitable technology, then being able to tell NGOs, don't waste your money in wind and use it on another technology which is suitable. So to do that, we need to build up a knowledge database from member organisations, have a database of how much it costs to install a wind turbine, a list of suppliers, different business models where success and failure are, and different financial and institutional models from the Wind Empowerment Network to learn from other people's mistakes and successes. And from that, recruit and build a network of experts to be able to offer this consultancy. I've run over slightly, but there's some references there for anybody that wants to know where the information came from, and that's my presentation.
Thank you for that, Aran.
Are there any,
very useful information. Oh, go ahead.
Are there any questions?
Hello.
Hi.
Can you hear me? Hi. So, Aran, thank you. That was a fantastic presentation, an amazing way to revitalise the Wind Empowerment webinar series. So, thank you for volunteering and taking the first stab at it. I think that was the best start we could possibly have given it. And Jessica, thank you for organising the event, because a lot of the stuff that you've done has been behind the scenes, but in order to make this event happen, you've put in a lot of work. So, thank you to both of you. With regards to the content of the presentation, Aran, I thought it was an excellent discussion of the challenges that are faced in Ethiopia with the technology, that many of those challenges are replicated elsewhere. So I think it's something that will be very useful for other people looking to build and install small wind turbines in other developing countries, because there's a lot of lessons that are transferable. I really like the methodology that you used. Obviously, I mean, we worked closely on the methodology, but I think you've done a great job of developing it a lot further by including hybrid systems, by looking at productive uses of energy, and by including other factors. Like I think the map that shows civil unrest is a really important factor that would often be forgotten, but I think it's really important because it has huge implications for future projects in the country. It means that the most viable region for the technology, unfortunately, is the most unstable one. I did have a specific question, actually, about when you were showing the graph of the correlation between the solar and wind resource in 2 different areas in the country. And there's one in the west where it seemed that the solar and wind resources were available at different times of year, and one in the east where the solar and wind resources were available. Sorry, I've mixed them up. In the west, they're available at the same time of year, and in the east, at different times of the year. But I just wanted to note that the difference in the solar resource on that graph was actually quite small. It was only one, I think, maybe 20% difference. So that means you'll get a 20% difference in energy yield, which is not very much. But on the wind resource graph, then it went between something like 4 and 7 meters per second, which, as we all know, is a huge variation. So the wind resource goes from just about enough to way in excess, whereas the solar resource goes from a lot to even more. And it comes down to that V3 that you were mentioning, in that the power produced by a wind turbine is proportional to the cube of the velocity, whereas the solar resource is only linearly proportional, or the power produced, the energy produced by a solar system is only linearly proportional to the resource. But I'm really glad that you included those graphs. It's something that I haven't necessarily done in my own work, but I think it's really important to think about not just how much energy do you get, but when do you get the energy. That's, for off-grid systems, probably one of the most important factors.
Yeah, thanks, John. Yeah, definitely. Homer lets you play around with that, and you can import several different seasonal profiles of wind and solar, and just run the simulation again and again to see what the different outputs is. And you're right, solar is linear, so a small increase or decrease in solar doesn't make that much difference, whereas the wind is exponential, so a small amount of increase in wind speed really affects the energy and the effectiveness of the system itself.
Yeah, something else I wanted to add, actually. You mentioned about how we should try and stop people wasting their time building wind turbines in places without any wind. So one thing that I've been thinking about doing for quite a long time now is that instead of, you mentioned going even more local, as in looking at the areas of high wind resource and then finding out which of those areas, like how much does it cost in each of those areas, what are the other factors that affect the viability of the technology right down at a local level. I've also been thinking at an even broader level, at the global level. So as Wind Empowerment, as the association, how can we decide which projects we want to support in the future? I think one of the most important factors should be what is the future potential of the technology in each region where we're supporting projects. So I think we should look at the whole world and think, what are the factors that make wind turbines work or not, like the number of lightning strikes, the wind resource, the solar resource, the vegetation. I'm here in Patagonia at the moment, and there's almost no trees here, which make it an ideal place for small wind turbines, as there's almost nothing to get in the way. So I think we should look at the whole world and look at in which countries or which regions can this technology work, and really look to develop projects in those areas. And then, as you say, go more local, go look at the national level, then look at the kind of the local area, and kind of go down from there, kind of increasing the resolution of the study each time.
Yeah, it'd be a good project for a PhD is a global market assessment for small wind turbines, and then highlighting potential areas that need to be looked at. But I think it's also collating information about what has worked and what hasn't worked with small wind turbines. And although wind speeds, lightning strikes, vegetation cover are all useful parameters, I think the main ones will probably be social aspects of how well were they looked after, what was the business model, how were they paid for. And I think cataloguing all of Wind Empowerment members' experiences for what's worked in the social aspect is just as important, and feed that into market assessments to have a look at the social aspects such as population density, government support, NGO support, community projects, number of cooperatives, that sort of stuff would be just as useful as the physical ones.
Any other questions out there?
I just want to add, sorry, yeah, I completely agree with what you're saying there, Aaron, but I think some of these factors that you mentioned, the social factors, can also be mapped. So say, for example, familiarity with mechanical or electromechanical components. So down here in Argentina, then lots of people already have vehicles, whereas if you're out in very rural Ethiopia, then many people will not have a motor vehicle. So that then already gives you a big head start on being able to perform maintenance locally, because if you've already got maintenance infrastructure there to maintain vehicles, then a lot of the tools and the skills are already there to maintain wind turbines, both at kind of the household level and at the kind of local level, as in if you've got a network of garages to repair car parts or car mechanics, then it's much easier to create a network of wind turbine mechanics. And if you've got someone who maintains their own car, then it's much more likely that they'll be able to maintain their own wind turbine, because many of the components are similar, like the bearing. I mean, and if you pick a turbine, it is actually a car bearing.
Yeah, absolutely. And as you saw, the road network really affects the cost of maintenance for getting components and getting supplies out there. So these are all things that can be mapped, I think, and then from that pinpoint where wind turbines are most appropriate.